Welcome to AI Paper Slop. Today we are looking at a paper called Visual Contrastive Self-Distillation, or VCSD.
Yep, by researchers from UMD, UCSD, Duke, and MBZ UAI.
Right. And we're going to just jump straight into the 60-second summary. So, on-policy self-distillation, or OPSD, for vision language models usually requires an external teacher, right? Or like privileged information such as ground truth answers or manual visual crops just to create an asymmetric learning signal.
Which is honestly a massive bottleneck.
Exactly. But this paper completely eliminates that need. VCSD uses the model's own internal contrast, comparing its next token predictions on an original image versus a blacked out control image.
And that boosts the probability of visually grounded tokens.
Right. And this method yields a massive 3 to 5% aggregate accuracy gain across Qwen 3VL and Qwen 3.5 models on 7 benchmarks. And it does this without any extra annotations or inference costs.
Which is wild when you think about it.
Totally. So if you are an ML engineer or an AI researcher listening to this, you know the constant battle, right? Finding scalable, annotation-free ways to ground VLMs and reduce those stubborn language hallucinations is, well, it's one of the hardest problems right now. That makes this paper highly relevant to what you're probably working on.
Yeah, I mean, to really get into the mechanics of what VCSD is doing, we sort of have to start with the baseline of standard on-policy distillation.
Okay, let's set the stage.
So normally you have a student model generating a response, and you use a smarter, usually much larger external teacher model to give you dense token-level supervision.
Right, along that exact same generated trajectory.
Exactly. And this works well because it explicitly aligns the training with the student's actual inference time distribution. You avoid those weird distribution shifts that happen with off-policy data.
But the catch is that dependency on a massive external teacher.
Huge catch. It introduces like crazy post-training costs, latency, just massive computational overhead.
Which is why everyone wants to move to on-policy self-distillation. You just drop the expensive external teacher and use an exponential moving average, or EMA, version of the student model itself.
Right. The EMA weights act as a slightly more stable teacher.
Yeah.
But mathematically, that setup creates a wall.
Because they're too similar.
Yeah. If the student and the EMA teacher are processing the exact same prompt and the exact same image at the exact same prefix step, the teacher isn't giving you any genuinely new information.
The gradient signal just sort of flatlines.
Precisely. The literature calls this the need for asymmetry. You have to make the teacher more informative than the student, even though they share practically identical weights.
And the current methods for manufacturing that asymmetry are, honestly, basically just manual band-aids.
Oh, completely.
Like, for language reasoning, you feed the teacher privileged ground truth answers. For vision language tasks, you feed it visual evidence.
Right, passing bounding boxes or specific high-resolution crops.
Yeah, exactly. You're hand-feeding the relevant visual data to the teacher model while keeping the student blind to it.
And while those methods do force an asymmetric signal, they depend entirely on task-specific pipelines. If you're doing general multimodal processing in the wild, you don't always have a pipeline to generate perfect visual crops.
Right.
It requires external object detection models or, manual human annotations just to set up the training loop.
Wait, but if we're relying on humans to draw bounding boxes or relying on completely separate object detection models just to train the teacher, doesn't that completely defeat the self in self-distillation?
It 100% does.
It totally kills scalability. Like, if the whole point of a self-improvement pipeline is to scale compute without scaling human labor, being bottlenecked by manual annotations means we are losing the entire advantage.
It completely ruins it. And that fundamental contradiction is the exact motivation for this paper. The authors essentially asked, can the asymmetry we need be constructed purely from input conditioning?
Without any auxiliary data at all.
Right. No extra annotations, no external models. And they found a way to do exactly that. The core innovation of VCSD is deriving target asymmetry purely from matched visual conditioning.
Okay, let's break down the mechanics of this matched visual conditioning, because the process revolves around what we can basically call a lights out trick.
Yeah, the pipeline is incredibly elegant. First, the student model generates an on-policy response prefix, just normal stuff. Then, the EMA teacher evaluates that exact same prefix twice.
Okay, twice.
Run 1 is with the original image. Run 2 is with a content-erased control image. By default, they just use a pure black RGB image.
Ah, okay. So we aren't just sending like a null input or bypassing the vision encoder entirely.
No, not at all. We are keeping the exact same tensor shapes, the same multimodal input interfaces, and the exact same visual token counts. The parameter pathways are identical.
We are just zeroing out the semantic pixel data.
That is the critical engineering detail, yeah. The computational path remains completely undisturbed. The only variable changing between run 1 and run 2 is the visual content itself.
Wow.
Okay, so then we look at the tensor math. At each token generation step, they calculate the token-wise log probability difference. They call this delta T of V. You simply subtract the log probability of the black image from the log probability of the original image.
So by subtracting the prediction made in the dark from the prediction made in the light, you isolate the direct mathematical impact of the visual data.
Exactly.
It's like asking someone to describe a complex room and then suddenly turning off the lights mid-sentence.
I love that analogy.
Right. Like if they keep describing objects perfectly in the dark, they aren't actually looking. They are just reciting from memory or, relying on language priors. But if they stumble or stop, it means they were genuinely using their eyes. We want to reward the tokens that rely on the lights being on.
And if a token's probability drops significantly when the lights go out, that tells us the token is highly grounded in the actual image. What VCSD does mathematically is create an implicit visual evidence reward from the model itself.
That is so clever.
It really is. That conditional log ratio actually approximates the point-wise mutual information between a candidate token and the observed image.
But wait, let's follow the lights out analogy for a second because I feel like there's a massive potential flaw here.
Okay, let's hear it.
If we strictly reward tokens with the biggest probability shift when the lights go out, couldn't the model just hallucinate highly densitive but completely irrelevant words?
Oh, like what?
Like, what if someone in the dark suddenly yells, "Zebra!" with a huge probability shift, but there's no zebra in the room? They wouldn't have said zebra with the lights on, so we shouldn't reward that. Doesn't this raw contrast math just encourage volatile gibberish?
It absolutely would. And that is a major pitfall in standard contrastive decoding. Naively amplifying the contrast delta boosts rare volatile tokens that have no semantic relevance.
So how do they fix that?
To solve this, the researchers introduced what they call the relative plausibility support. It's governed by a parameter, beta, which they set to 0.1.
Okay, and how does beta act as a filter?
It forces the model to use the original image distribution as a strict plausibility anchor. The contrastive shaping is only applied to candidate tokens that the model already considers highly likely based on the original image.
Oh, I see.
Yeah, it basically masks out the contrast scores for any token whose original image probability is less than beta times the maximum token probability for that step.
So going back to the room, if zebra wasn't already a highly probable candidate when the lights were on, its massive contrast score when the lights go off is just ignored completely?
Precisely. The original image prediction gives you the pool of plausible candidates, and the contrast score just sharpens the preferences among that specific, sane group of tokens.
That completely prevents the model from derailing into irrelevant vocabulary.
Exactly. So once you have this sharpened, visually informed target distribution, the next step is passing it back to the student model.
Right, the actual distillation part.
Yeah. The target is distilled into the student using a full distribution forward KL divergence. And the choice of divergence function here is really critical. During their ablations, they tested using reverse KL and Jensen-Shannon divergence too.
And forward KL won out consistently, but why? Why does the direction of the KL divergence matter so much when distilling these specific distributions?
It comes down to the difference between mode covering and mode seeking behavior. Forward KL divergence is mode covering. It penalizes the student heavily if the student places zero probability mass where the teacher target has mass.
So it forces the student to stretch out and cover the entire reshaped probability landscape.
Exactly.
Whereas reverse KL is mode seeking, meaning it penalizes the student for putting mass where the teacher has zero mass.
Right. When you use reverse KL, the student gets terrified of exploring, so it tends to just collapse its predictions onto the teacher's single highest probability peak.
But in VCSD, we aren't just trying to teach the student a single correct answer.
No, we've carefully reshaped the entire distribution to boost all the visually grounded tokens. If the student collapses onto just one token, you lose the diverse visual reasoning we just spent all that compute trying to calculate.
That makes total sense. Forward KL ensures it respects the full landscape. Okay, so the pure black image works beautifully as our lights out condition. The math holds up. But I want to look under the hood at the ablations.
They did some really interesting tests there.
Yeah, because what if the image isn't perfectly black? What if we use a blurry image or like TV static? Does the method just break down?
You would think so, but no. Instead of a black image, they tested Gaussian noise, Gaussian blur, and even passing literally no image at all, just bypassing the visual tokens.
And what happened?
Surprisingly, they all perform practically the same.
Which proves it's not about the specific degradation process at all.
Exactly. It synthesizes a core truth about how VLMs work. The efficacy of VCSD is just about the removal of instance-specific content. Black pixels, static noise, aggressive blur. You are just erasing usable visual information while keeping the tensor shapes and token counts matched.
That erasure is what creates a reliable zero information baseline.
Yep.
Okay, let's talk about the anchor. We established that the original image prediction acts as a plausibility anchor, which the paper represents mathematically with lambda. What happens if you remove that anchor? Like if lambda equals 0,
Well, the aggregate accuracy actually stays somewhat decent.
but if you look at the charts, there is a massive spike in language drift. Why does isolating the visual contrast cause the language model backend to start spitting out gibberish?
To understand that, you have to look at the tension between visual tokens and syntactic LLM priors. Language drift here basically means the model outputs non-target language tokens or just loses grammar.
Right.
If you rely purely on the visual contrast, you run into a grammatical problem. Filler words like B is A, don't have high visual contrast.
Oh, because their probability doesn't change much, whether the lights are on or off?
Exactly. They are structurally necessary but visually irrelevant. So if we only reward tokens with high visual contrast, the model essentially starts penalizing the grammatical glue that holds sentences together.
It would just start yelling a disjointed list of visual mounts. Table, red, apple.
That is the exact mechanism of the drift. The original image anchor, lambda, forces the target to stay close enough to the original prediction to maintain the grammatical rules of the LLM backend. It keeps the model fluent, while the contrast signal teaches it to rely on its eyes for the actual subjects and adjectives.
That is such a delicate balance. And speaking of balance, what about how hard we push that contrast signal, the alpha parameter?
They found a very definite sweet spot for alpha. Setting the contrastive strength multiplier between 1.0 and 1.5 is ideal.
And if you push it beyond that?
If you push it to 2.0, the performance actually degrades right back down to the baseline. You end up overwhelming the teacher's foundational knowledge. Moderate contrastive shaping is highly effective, but it requires that exact balance.
Okay, so the architecture makes sense, the math is sound, and the ablations show it's robust. But does this actually translate to better performance across different model sizes? Let's run through the empirical numbers.
Yeah, because for a zero annotation method, the numbers are seriously impressive. They evaluated VCSD on Qwen 3VL and Qwen 3.5, scaling from 2 billion up to 9 billion parameters.
And they ran evaluations across 7 rigorous benchmarks, right?
Right. BLAnc, MMStar, MathVista, VBench, and a few others, just to ensure the gains weren't isolated to one specific task.
The results for the Qwen 3 VL to B model are a perfect snapshot of this. The aggregate accuracy jumped from 62.27% on the base model to 67.04% using VCSD.
A near 5% jump.
And what's crucial for anyone deploying these models is that this showed consistent gains across all categories: general perception, complex visual mathematics, and most importantly, hallucination reduction.
That consistency is the real takeaway. It consistently outperformed both the unmodified base models and the standard OPSD baselines that rely on privileged answers. It definitively proves that input-conditioned asymmetry works perfectly.
To really ground this, there's a qualitative example from the paper on the MathVista benchmark that perfectly illustrates this.
Oh, the base 10 blocks problem.
Yes, the image is a math problem involving base 10 blocks. You have to calculate the total number represented, and the answer depends heavily on accurately counting a stack of large 1,000 cubes.
And visual counting is notoriously difficult for standard VLMs. They tend to guess based on context patterns rather than actually counting the visual instances.
Exactly. The base model completely misinterprets the blocks and guesses 6169. Standard OPSD, trained with privileged answers, overestimates and guesses 8519. But VCSD gets it exactly right.
It correctly identifies the 7,000 cubes and predicts the ground truth answer of 7,519.
Right. And why did it get it right?
Well, if we look at figure 6 in the paper, it mathematically explains it. The researchers visualized the Koken-level image-dependent contrast scores. They show another example with a food stall with an awning.
Where they ask about the color of the awning.
Right. And when you look at the heat map of the contrast scores, VCSD specifically boosted highly visual concept tokens. Words like shingles, beige, and sign received much stronger positive contrast compared to the base model.
It concentrates the probability mass on truly image-grounded evidence. It forces the model to look at the fine details rather than relying on an LLM backend to just guess.
Exactly. It limits the hallucination problem at the source.
So wrapping this up, what does this mean for the listener? VCSD offers a highly scalable, compute-efficient way to train vision language models to actually look at images. It acts as a clever hack to extract an implicit visual evidence reward from the model itself.
Using nothing but the original prompt and the image.
No external teachers, no human-annotated bounding boxes, just pure self-contained distillation.
And, if we abstract a core concept of this paper, it raises an incredibly provocative thought for the future.
Oh.
If this contrastive trick works by comparing a full visual state to an empty one, could we apply a similar temporal contrast to agentic workflows?
What do you mean?
Imagine an AI agent navigating a UI. Could we mathematically contrast the model's internal state before and after observing the consequence of an action to isolate and reward truly action-grounded tokens?
Oh, wow.
Right. The concept of internal contrast as an annotation-free supervision signal extends far beyond static images. It could literally be the key to self-improving agents.
That is a fascinating architectural idea for everyone to mull over, applying the lights-out trick to temporal agent states. Well, thank you all for tuning in to AI Paper Slap. Be sure to check out the VCSD paper for the full mathematical breakdown. Until next time, remember, if you really want to know if your model is looking at the room, you just have to turn off the lights.